Hello everyone, and welcome to our video on the Cartesian graphs of sine and cosine. So for this video, our goal is just to take the information for the sine and cosine functions that are given by the unit circle and use it to build a Cartesian plane visualization for the functions. So as a reminder, Cartesian plane is just our normal xy plane. So right now, what we have, our main visualization tool for sine and cosine is as our x and y coordinates on the unit circle, which is how we define those functions. But when we want to think about the long-term overall behavior of sine and cosine, it helps if we change to the Cartesian graph of the function. So first we're going to just take a look at a couple properties. We're going to review a definition from a while back, and then we're going to take this information, tie it all together, and use it to draw the graphs for sine and cosine. So first, definition, a function f is called even if f of negative x equals f of x for all x. That is, the function is symmetric about the y-axis. So as a reminder, in a picture, what this means is that if I have an x value and the negative of that x value, I get the same y value for both points on the graph. So fact, cosine is an even function, meaning that cosine of negative theta equals cosine of theta. And we can see that on the unit circle. If we draw theta and we draw negative theta, the x coordinate is the same for both of those angles. So cosine of both of those angles is the same. Okay, and as another reminder here, definition, a function is called odd if f of negative x equals negative f of x for all x. That is, the function is symmetric about the origin. Right? So, in other words, when I plug in x for the function, I'll get some y value. And then when I plug in negative x, I should get the negative of whatever that y value was. So you get this symmetry about the origin, which basically looks like you've rotated the right half of the graph 180 degrees. So fact, sine is an odd function, meaning sine of negative theta equals negative sine of theta. All right, well, how do we see that? Again, we look at the unit circle, and when we look at theta, right, we get xy. Y is my sine of theta value. When we look at negative theta, what do we get? We get the negative value of y, right? We get the same triangle gets formed here. But this triangle on the bottom is, well, on the bottom. So the y value is in the negative direction. So, in other words, sine of negative theta equals negative sine of theta. All right, and another definition here. F of x is called a periodic function if f of x plus p equals f of x for some real number p, meaning that all x values work with this value of p. So if I take any x value and I add p to it, I get the same y value out. So the smallest such p is called the period of the function. And fact, sine and cosine are periodic functions with period 2 pi, or 360 degrees. So again, the important question is always why? And just look at the unit circle. If I start with the angle theta, and I add a full circle, I add 2 pi to that theta, I end up back at the exact same coordinates, so I get the exact same values for x and y. In other words, cosine of theta equals x, and cosine of theta plus 2 pi equals x. So cosine of theta equals cosine of theta plus 2 pi. So 2 pi is the period for cosine, and likewise, it's also the period for sine, because we get the same y value there as well. Okay, so now we're going to start taking all this information that we've got, and we're going to use it to graph sine of x. So first, we're going to just take note. What do we know? We know the period is 2 pi. That means this graph is going to repeat its behavior every 2 pi. And we also know that sine is an odd function, meaning that sine of negative theta equals negative sine of theta. And the way I'm going to graph this Cartesian plane is by taking the information off of the unit circle and just plotting it on to the Cartesian plane in our standard XY format. So we'll just real quick sketch out a unit circle here. We're not going to draw everything. All we're going to draw is the key quadrant points. So what do we know our X and Y values are here? 1, 0, 0, 1, -1, 0, and 0, -1. And of course, remember that sine is the Y value on the unit circle. So now we can pretty quickly plot these points, right? And this is a skill that for dealing with these graphing sine and cosine functions and the transformations of these functions, we want the initial graph to be something we can do really quickly, because otherwise we're going to spend a whole bunch of time every time we need to graph these things that we don't really want to have to spend. So if I just think about these y values on the unit circle, I know sine of 0 is 0, and sine of pi over 2 is 1, and sine of pi is 0, and sine of 3 pi over 2 is -1, and sine of 2 pi is 0. And so that's my first 2 pi for my graph. So again, that should only take a few seconds if you know these quadrantal values on the unit circle. And so with that, what else do I know? I know the period is 2 pi, which means this graph is just going to repeat the same behavior the next 2 pi. And that's going to happen in both directions, right? So I could just repeat this backwards. I'll do some little half pi marks here. But I also can use the fact that sine is odd. So at the origin here, it's going to be like I rotated my graph 180 degrees. Either way, we see that the graph for sine should go like this once we're moving towards the left. Well, that got a little sloppy there. Let's try that again. There. And of course, this graph, any angle works on the unit circle because you can just keep circling. So we can send this graph as far in either direction as we want. That'll be fine. But this is enough. Okay, so that's our graph of sine. Okay, now let's graph cosine. So again, when you go to graph cosine, this should be something that you can do really quickly because you know the quadrantal values for cosine, right? We look at these points and it's 1, 0, 0, 1, -1, 0, and 0, -1. But this time we're looking at cosine, and cosine is the x-coordinate on the unit circle. So let's go ahead and plot it. Cosine of 0 is 1. Cosine of pi over 2 is 0. Cosine of pi is -1. Cosine of 3 pi over 2 is 0. And cosine of 2 pi is 1. Now, the values in between, I kind of glossed over this. It gives us like a bit of a smooth curve here, but it's not really circular, even though it might kind of look like that. You could get a better, more accurate shape of your graph by plotting the individual angles in between, but that's not super valuable for the purpose of this exercise, which is to give us the sort of long-term visualization of what these functions are doing. So, with that being said, all right, I'll add 2 more extra marks here. Cosine also has period 2 pi, so I can just repeat this exact pattern for another 2 pi. And cosine is an even function, meaning cosine of negative theta equals cosine of theta. And that means I just get a mirror image over the y-axis. So I can just draw that out that way. And again, these functions are defined for all real numbers and they're periodic, so I could keep drawing this out in either direction for as long as I wanted. Okay, so, well, what's the big deal? Why do we care so much about the Cartesian graphs of these functions? Well, it should be actually kind of clear in their very shapes, right? The cosine functions and sine functions are waves. So anything that we model with waves, whether it's electromagnetism, right? Radio waves, the actual physical waves on the beach, all of those kinds of functions can best be described as combinations of our sine and cosine functions. So that's the big value here of visualizing these as Cartesian graphs. Now, of course, you have to do transformations on these graphs of sine and cosine, but we already know how those transformations work. We know how to shift left and right, up and down. We know how to stretch vertically and horizontally. So all those transformations that build the myriad of wave shapes in the real world are all things that we can do by just manipulating our sine and cosine functions and combining them in various ways. So let's just take a look at a summary of some of the properties of our sine and cosine graphs. So again, these are just the sine and cosine graphs drawn a little neater. Have a little computer algebra system do it for me. But again, it's all those key points, right? So just like I've said before with previous graphs, we don't just graph a ton of points. That would be a big waste of time. We graph the key points, the points that are easiest to evaluate quickly and give us the idea of the shape. And for sine and cosine, the easiest ones to evaluate are the quadrantal angles, 0, pi over 2, pi, 3 pi over 2, and 2 pi. And then we can just use the 2 pi period to give us the repeat of our graph in either direction. Okay, so when we look at the properties here, what do we see? Well, of course, we already know that the domain and range for sine and cosine is negative infinity to infinity. We can plug in any angle we want into those functions. We already know the range for sine and cosine is negative 1 to 1, because we know the output for sine is the y-coordinate on the unit circle, and that y-coordinate has to be between negative 1 and 1. And we know for cosine, the output is the x-coordinate on the unit circle, and we know that output has to be between negative 1 and 1. Now, what else do we know? We know the zeros of these functions. We know that our zeros for sine occur at 0 and pi and 2 pi, so forth and so on. So that's an integer multiple of pi, right? So n here is just an integer, meaning 1, 2, 3, 0, negative 1, negative 2, so forth and so on. And the zeros for cosine start at pi over 2, and every time you add a multiple of pi or subtract a multiple of pi, you get another 0. So again, this just looks like pi over 2 plus any integer multiple of pi. Okay, where do the maximums occur? Well, if we take a look at the graph of sine, we see a maximum at pi over 2. And the next maximum occurs 2 pi past that. So the maximums occur only every 2 pi, as opposed to the zeros, which occur every pi. The maximums occur every 2 pi. And so for sine, our first maximum can be thought of as the maximum at pi over 2. And then we add integer multiples of 2 pi. And for cosine, our first maximum occurs at 0. And then we can think of our other maximums as being multiples of 2 pi. 0, 2 pi, 4 pi, negative 2 pi, so forth and so on. And when we look at the minimums, so the minimums are when sine or cosine are negative 1 in this case. So for sine, the first positive minimum we see is the minimum negative 1. I should say the minimum is negative, but the first positive x value associated with that minimum is 3 pi over 2. And we could subtract 2 pi, that gives us another minimum, or we could have added 2 pi to get to another minimum. But again, we see that our minimums are 3 pi over 2 plus any integer multiple of 2 pi. And for cosine, the first minimum we see is at x equals pi, and the minimum is negative 1. And so if we add 2 pi, we'll get to 3 pi, that'll be another minimum. Or if we subtract 2 pi, we'd be at negative pi, that's another minimum. So all of our minimums for cosine are at pi plus integer multiples of 2 pi. And again, we know that sine has odd symmetry, cosine has even symmetry, and the period for both of these functions is 2 pi. Okay, so we're going to introduce another definition here. Let f be a periodic function. Suppose that m is the maximum value of f and little m is the minimum value of f. Then the amplitude of f is defined by 1/2 of the difference between big M and little m. So that seems like a strange definition, but amplitude just means the distance from the center of the graph, vertically speaking. So the distance is given in this case by 8 minus 2, right? So my amplitude is 1/2 of the distance between 8 and 2. So 8 minus 2 is 6, 6 over 2 is 3, right? That's the idea there. Now, oftentimes, it's much easier to find the amplitude from the formula than to have to go through this. But if we have a function that's been vertically shifted up or down, and all we've got to work with is like the graph, and we don't have some trick to use with the formula, then we really, in order to figure out that amplitude, need to think of it in terms of this more precise definition. Okay, so what about when we do have a nice formula? So we've got the formulas y equals a sine of x and y equals a times cosine of x. So in the case of these formulas, the absolute value of a is going to be the maximum of both of these functions. That should make sense because the maximum value for sine is 1, the minimum value is -1. So if a is positive, a times 1 is a. If a was a negative number, you'd take -a times -1, and that'll give you a. In either case, you get the absolute value of a. And the absolute value of a will be the minimum of both of these functions, similarly. So how do we get the amplitude? Well, if we just apply our formula, big M minus little m, that's 1/2 the absolute value of a minus the negative absolute value of a. But minus a negative is a plus, so that's 2 times the absolute value of a times 1/2. And 1/2 times 2 is 1, so that's just the absolute value of a. In other words, if we're looking at y equals a times sine of x or y equals a times cosine of x, then the amplitude is just the absolute value of whatever a is, and hence the range of these functions that are being multiplied by a will be between negative the absolute value of a and the absolute value of a. Okay, so let's take a look at a graph to see what that looks like. This is essentially just a vertical stretch, which we already know how vertical stretches work, right? So we've got the graph y equals sine of x. If we do a vertical stretch, we multiply all of our y values by 2. So before, when we had 0, 0 times 2 is still 0 here. But when we multiplied the y value 1 by 2, we go up to 2. So your maximums will stretch up to 2. Your minimum will stretch down to -2. And the graph stretches vertically across the whole thing accordingly. So if the absolute value of a is greater than 1, we call this a vertical stretch. And if the absolute value of a is less than 1, of course, we call it a vertical compression. Okay, so here we've got a vertical compression by 1/2. And again, it's the same idea. You're just taking the previous y values of the blue graph, multiplying them by 1/2. So your zeros stay 0, your ones become 1/2, and your -1 becomes -1/2, and all of your other y values compress down accordingly. Now, we also got to talk about horizontal compression and stretch. So here we're looking at multiples of the x value, just like any other horizontal compression or stretch. So again, all these things with sine and cosine functions, they work the same way that they work for all other functions. When you multiply x by a value, it's going to cause either a stretch or compression, depending on the value of that constant. So if the absolute value of b is greater than 1, then we say sine of bx experiences compression by a factor of 1 over b. And if the absolute value of b is less than 1, sine of bx and cosine of bx experience a stretch by a factor of 1 over b. So in both cases, the new period for each function is p equals 2 pi over b. Now, I want to make sure that everybody understands why we get this new period of 2 pi over b and why this causes the compression and stretch in the direction it does. So let's think about it this way. If I have y equals sine of x, or let's say sine of theta here, one period for sine of theta is how long it takes theta to move from 0 to 2 pi, right? 2 pi is the period, so sine of theta will repeat its behavior every 2 pi. So one period is just the distance from 0 to 2 pi. So if I take y equals sine of b times x, the key thing is that one period is still the distance for my input to go from 0 to 2 pi. The difference is that my input now is b over x instead of just theta. So if I divide everything by b here, what do I get? I get x is between 0 and 2 pi over b. But the distance between 0 and 2 pi over b is by definition the period, right? So the period for my new x value is 2 pi over b. So, in other words, what we're saying is the input is going from 0 to 2 pi, but my new x values only need to go from 0 to 2 pi over b to make the input go from 0 to 2 pi. So that's why our period stretches or compresses to 2 pi over b. So if we take a look at this graph, y equals cosine of x in blue, and y equals cosine of 2x. So what's the new period? Well, the new period is 2 pi over 2, which is pi. So the easiest way to think about this is that you draw your period from 0 to pi now, and you mark your 4 key points, or I should say 5 key points, right? So cosine starts at 1, then goes to 0, then -1, 0, and 1, and it does all that same behavior the blue graph did, but it does it from just 0 to pi instead of 0 to 2 pi. Now similarly, if we look at the graphs y equals cosine of x and y equals cosine of 1/2 x, all right, what do we get for our period? We get 2 pi divided by 1/2, and divided by 1/2 is multiplied by 2, so this is really 4 pi for my period. So one period for cosine is from 0 to 2 pi, and one period for cosine of 1/2 x is 0 to 4 pi. So again, when I think about this, let's look at the graph of cosine. It goes 1, 0, -1, 0, 1. That's one period. So when I look at the graph for cosine of 1/2 x, it goes 1, 0, -1, 0, 1 over one period. So if you divide up your period evenly into 4 sections, which makes 5 total points that you're going to plot, then it's very easy to replot this graph in terms of the new period. Okay, so phase shift. Again, a phase shift is just a horizontal shift. So it's we give the special name phase shift to refer to wave functions like cosine and sine, because we talk about phases in the applications of those things, right? Like you may have heard terms like your audio signal is out of phase, meaning that there's some interference going on. So we use that term interchangeably, though. When we're talking about wave functions, phase shifts and horizontal shifts are really the same thing. Now, they work exactly the same way. So we've got the graph cosine of x and cosine of x minus pi over 2. If I take my new input, x minus pi over 2, set it equal to 0 and solve it, x equals pi over 2. So this is a shift right by pi over 2, which is exactly what we have on our graph here. Our orange graph is just the blue graph shifted to the right by pi over 2. Okay, so let's actually do some examples of some graphing. So one of the things that I want to emphasize a lot is that we have a really nice benefit with sine and cosine functions, which is that since these functions are even and odd, sine is an odd function and cosine is an even function, then we don't ever have to deal with reflections across the y-axis, because if b is less than 0, and I'm talking about when we look at the form, say, sine of bx, if b is negative, I can always use an odd property for sine or an even property for cosine to rewrite the function into a form that's actually going to be easier to graph. So anytime you have a negative inside sine or cosine and you're trying to graph these functions, I strongly suggest that you first use even and odd properties prior to graphing. So with that in mind, let's go ahead and do that for this example. So remember that sine of negative theta equals negative sine of theta. That's my odd property for sine. So I'm going to take this sine of negative 2x and rewrite this as a negative sine of 2x. Okay, so now when I go to do my first transformation, I've already put the graph of sine here. But again, you should be able to plot this very quickly. Sine of 0 is 0, sine of pi over 2 is 1, sine of pi is 0, sine of 3 pi over 2 is negative 1, sine of 2 pi is 0. Boom. Connect the dots, and then repeat it every 2 pi. That's your graph of sine. All right, so we've got the graph of sine. Now we're going to do our transformations one step at a time, like always. So first we're going to go to y equals sine of 2x, since that's the closest thing to the x. Inside parentheses, we're multiplying by 2. And how do we get our period? Well, I'm always going to just go through that little extra step, saying our normal period is 0 to 2 pi, but our new input is 2x. So that means x goes between 0 and pi. So my period is pi. And of course, you can think of the period as being a horizontal compression in this case, because we're taking the bigger period of 2 pi and shrinking it down to a period of pi. So here's what I'm going to do. I'm going to take all of my space from 0 to pi. Now notice from 0 to 2 pi, I have 4 marks on my graph, other than the y-axis. So from 0 to pi, I want to have 4 marks on my graph. That means my center mark here is pi over 2, right? And the other ones will be pi over 4 and 3 pi over 4. And all I'm going to do is take the same points that I have, right? But I'm going to plot them at these new dividing marks here, right? So we just take, instead of having 2 pi divided into 4 intervals, we divide pi into 4 intervals, and we mark our points over that shorter distance, and then that gives us the graph of this thing compressed down to period pi. Now, of course, you can mark this graph out further. I'm not going to go crazy here. I think 3 repeats of the graph is more than enough. Okay, and so now our last transformation is just going to take us to y equals negative sine of 2x. And that's nice and easy. We're taking our previous y value, multiplying it by negative 1. That's going to reflect the y values over the x-axis. This is a reflection over the x-axis. So I'll draw my new graph. And all the zeros are going to stay the same, of course. So I'll just plot those zeros first. I don't necessarily have to plot them all first, but... And then anywhere I had a peak, that's going to be down at the bottom, right? Any of those maximums. And then the minimums are going to flip upwards. And that's it. That's our graph of y equals negative sine of 2x. All right, so now we'll look at the full form of the transformations for sine and cosine. So if we have an expression inside sine or cosine, and we want to interpret all of our transformations kind of at once, then to do that, you want to make sure that you factor your expression inside, so that if you had a common factor, you factor it out so that you just have x plus or minus something in parentheses with a factor multiplied in front. It's going to be really important, or you will be very likely to misinterpret the transformations in this form. Now, one little thing I want to note is that we are assuming here that b is greater than 0. And if b is not greater than 0, if you have a negative value for b, you always want to use that even or odd property like we did in the previous example. Okay, so here, what do we get? A is our amplitude, assuming it's positive. I really should say the absolute value of A is the amplitude. B is the horizontal compression and stretch, right? So it's really, you get the period of 2 pi over B. Your compression or stretch will be the factor 1 over B. And C is your horizontal shift. That dictates the horizontal shift. And that should make sense, because if I take B times x minus C, set it equal to 0 and solve it, when I divide by B, I get x minus C equals 0 and x equals C. So C is the horizontal shift. H is our vertical shift as always. We're taking the old y value and adding H. And again, our period is 2 pi over B. So here I've graphed a little past one period of cosine, because I'm not going to do a whole bunch of repeats of the period every time. That's not necessary. But we're going to sketch this graph y equals 3 times cosine of x plus pi over 3. So first thing I want to figure out is, what is my horizontal shift? Well, it's negative pi over 3, but again, it's always best to think of this, to avoid making misinterpretations, as setting your input equal to 0, solving it. So if I go to y equals cosine of x plus pi over 3, that's going to be a shift left by pi over 3. And that can be a little bit tricky to graph, because our previous graph is marked at all of the pi over 2 points, right? So how can we graph that? Well, what I'm going to do is mark all of the pi over 2 points again, and I've made my graph a little bit larger here. And I'm going to mark points that are about 1/3 of pi to the left of each of them. All right, 1/3 of pi is less than 1/2 of pi, but more than 1/4. Now, if you need to figure out what the actual x values are here, you can always do the arithmetic off to the side, right? Like pi over 2 minus 1/3 of pi. That's 3 pi over 6 minus 2 pi over 6. That's pi over 6, right? So this first point, for example, is pi over 6. And you could repeat that process, pi minus 1/3 of pi, so forth and so on. But it's not really necessary to get the graph of this correctly. It's not necessary to do that. So I'm just going to mark them roughly, because we just need a rough visual approximation. All right. And now I take each of my points and I shift them left by that mark, right? So my point from my 1 will go to this orange mark. My point from my pi over 2, which was at 0, it's going to go here. And then the one that was at pi will move here. The one that was 3 pi over 2 moves. Oh, that should move. Hold on. Those last two didn't make any sense. Let's try that again. All right, the one that was at pi was -1, right? Pi -1. Move that to the left. The one that was at 3 pi over 2 was 0, so I move that here. one that was 2 pi was at 1, so I move that left, and now I can connect my dots. So forth and so on. Okay, so that's my shift, and now our last transformation for this one is just the amplitude transformation, right? I'm multiplying the y values by 3, and so we'll think of this as changing the amplitude. The absolute value of 3 is 3. So there's no significant difference here in my graph, except that I'm going to take all of my peaks and move them to 3 and -3 accordingly. So I'm going to mark those half spots again in black and mark all those shifted points in orange. And then, okay, here I had a peak at this first mark here, so that's going to move up to 3. And here I had a 0 at this orange mark, so that's going to stay 0. And here I had a -1, so it's going to go down to -3. And then 0, and then 3. And then over here it'll hit 0 again. All right, picture doesn't have to be perfect. It just has to be good enough to interpret the information from it. And of course, these graphs just keep going on forever and ever. Okay, so that's that transformation. That gets us to our final form of the graph, which is y equals 3 cosine of x plus pi over 3. So the key thing is, I'm hoping that it's clear that everything we're doing here is the same transformations we've been doing with functions before. The difference is just in terminology, right? When we talk about amplitude, that's really just vertical shift. It's not any, or vertical stretch, I mean. It's not any different than the vertical stretching and compressing we were doing before. When we talk about phase shifts, that's the same thing as a horizontal shift left or right. So it's all the same ideas, and we graph these things the same way we did all of our previous transformations. Okay, so now we're just going to take a look at a few more quicker questions here. So first, find the amplitude, period, and phase shift of y equals 10 cosine of 7 times x plus pi over 4. The key thing here is that this thing is already factored because we need to know what this b is for our period. Okay, so how do I find the period? Well, this is b, so let's do the period first. It doesn't actually matter what order we do this in. So period is just 2 pi over b. That's 2 pi over 7. Done. Okay, well, what about the amplitude? Well, the amplitude is just the absolute value of the number in front, and the absolute value of 10 is, of course, just 10. And now we need the phase shift, and like always, I recommend just setting this equal to 0 and solving it. I divide by 7. Oh, yay. That 7 in front doesn't matter because 0 divided by 7 is 0. But if we hadn't factored this first, then that would have caused us a real problem if we didn't work by solving that equation. So the phase shift is negative pi over 4, or left by pi over 4. Okay, now for example 4, we're asked to write an equation of the form y equals a times sine of b times x minus c, with amplitude 1/3, period 8 pi, and phase shift negative pi over 3. So in this factored form, all right, this is pretty straightforward. Amplitude is 1/3, so a equals 1/3. The period is 8 pi. So if the period is 8 pi, that means that 8 pi equals 2 pi divided by b. So if I multiply the b across and divide by 8 pi, I get b equals 2 pi divided by 8 pi. The pi's cancel, and 2 over 8 is 1/4. So b is 1/4, and phase shift is negative pi over 3. So remember, c is the opposite of your phase shift when you're in this factored form. So if the phase shift is negative pi over 3, then c is positive pi over 3. So when I write it in this form, I get 1/3 times sine of 1/4 times x minus c, which is pi thirds. Oh, wait, I already wrote that with the... That should be a plus. Okay. We wrote the phase shift in terms of c. So if the phase shift is negative pi over 3, I'm shifting left by pi over 3, so I need x plus pi over 3 in my expression. I'll just say it that way to be as clear as possible, right? Because if we take x plus pi over 3, set it equal to 0, that's x equals negative pi over 3. That's our shift. So our expression inside parentheses needs to be x plus pi over 3. Okay, so now let's take a look at this example 5. Write an equation in the form y equals a times sine of b times x minus c for the graph. Now, whenever you get a graph like this, you have to analyze the shift based on some key points. And that requires that you actually, take a look closely at how the graph is labeled. So usually in any problem like this, you'll see some points that are labeled really clearly like this. And the other key thing is you have to be thinking about what the original graph is, what sine is, so that you can think of your shift in terms of sine. So if I think of y equals sine of x, the Cartesian graph for this thing, right? Sine of 0 is 0, sine of pi over 2 is 1, sine of pi is 0, blah, blah, blah. Just need a quick sketch of this. And so I see for the graph of sine, I start at 0 and I go up. So where does this graph start at 0 and go up? Oh, it starts, the first 0 is here and it goes up from here. So that tells me I've shifted right by pi over 6. That's a shift right by pi over 6. Okay, so if my graph is shifted right by pi over 6, that tells me that my equation should look like a times sine of b times x minus pi over 6. You could take this input, set it equal to 0, you get x equals pi over 6. That's shift right by pi over 6. Now I need to find a and b, so I need to figure out what the period is. So remember, the period for sine is one full repeat of its values. So it should go from, its minimum all the way up to its maximum and back down again, right? So if I look here, I start at 0. This is my minimum. I go to 0. I go to the maximum. I go back to 0. I go down to this maximum. Okay, well, what is that? Well, it's not really marked clearly, so that's a little bit tricky. So let's think about it. If this goes to pi over 6, from the minimum to the 0, then that makes this next mark pi over 3, and the next mark pi over 2, and the next mark, each of these is pi over 6 apart, right? So this is pi over 2 plus pi over 6. Pi over 2 is 3 pi over 6 plus pi over 6. It's 4 pi over 6. That's 2 pi thirds. So in other words, the period is 2 pi thirds, right? Each subinterval was pi over 6, so 4 of them was 4 pi over 6 or 2 pi thirds. So if my period is 2 pi thirds, we'll do that work over here. Right, that should be equal to 2 pi over b. Oh, well, in this case, I don't even have to solve anything. 2 pi thirds equals 2 pi b. B is obviously 3. So now I've got y equals a times sine of 3 times x minus pi over 6. And finally, I need to know what a is. And the amplitude is just the distance from the center of the graph to the top or the bottom, which is 2. Now, how do I know that A is positive in this case? That's just because the graph was shifted over and wasn't flipped, right? When I look at this graph, if I shift over, I'm going up. When I shift over, I'm going up. So I didn't get a vertical flip over the x-axis, so A is going to be positive. Okay, so that's it for that one. And now we'll finish this up with one last example of graphing a function. And we're starting with our sine graph again. And of course, remember, you can always graph these on your own really quickly by just thinking sine of 0 is 0, sine of pi over 2 is 1, sine of pi is 0, sine of 3 pi over 2 is -1, sine of 2 pi is 0. Boom, 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 boom. Draw your graph. Done. That's your parent function. Now, as always, I want to do these transformations one at a time. So we're going to look at y equals sine. And for my preference, I'm going to rewrite this as -2 times sine of 4x plus 4 times pi over 2, which is 2 pi. Because I always prefer to think of the transformation occurring with the multiplication of x first, right? PEMDAS. All right, I like that multiplication to occur first. It would be okay to do the shift here first, but it does change how you interpret things slightly. So this is just my personal preference. So I'm going to look at sine of 4x. And so my period is 2 pi divided by 4, which is pi over 2. So I'm actually going to kind of stretch my graph out a little bit here. So instead of having pi over 2 really crunched here, since pi over 2 is going to be my whole period, I'm just going to stretch it a little bit. This would be pi over 2. This would be pi. And so remember, all the same behavior that happened from 0 to 2 pi has to happen from 0 to pi over 2. So I just break this thing down into 4 subintervals, just like my 0 to 2 pi was broken into 4 subintervals. And then I repeat the same pattern, 0, 1, 0, -1, 0. 0, 1, 0, -1, 0. And then all that pattern, of course, is going to repeat every period. I'm just going to draw 2 periods of this because any more than that would be a little too time consuming. Okay, so that's y equals sine of 4x. So if I just did y equals sine of 4x, now I've got to do the rest that's inside the parentheses. That's the 4x plus 2 pi. But remember, if we're thinking of our shift by taking this input, setting it equal to 0 and solving it, we get 4x equals -2 pi, divide by 4, x equals -pi over 2. So this is a shift left by pi over 2. And that's actually a really nice shift when you think about it, which you'll see momentarily. So I'm shifting left by pi over 2. But of course, my period was pi over 2. So shifting left by pi over 2 just shifts me back 1 repeat, which doesn't change anything about the shape of this graph. Because remember, even though I'm not drawing the whole graph, because that's not possible, right? This graph has period pi over 2, and it repeats forever. So since our phase shift happened to be an exact multiple of our period, our new period, we end up just getting the same exact graph. It doesn't change anything. Now you could think of, oh, well, I just took this point and I moved it that way by pi over 2. But of course, then it just ends up here, right? Ends up in the same spot. Okay, so now we have another transformation. Now I might make this graph a little bit smaller here, just so I have a little bit more room to work with. So we have two more transformations I want to do, and I don't want to try to cram them into one. So the next transformation is the multiple of 2. Y equals 2 times sine of 4x plus 2 pi. So multiplying by 2 gives me a new amplitude. The absolute value of A is 2, so my amplitude is 2. That just means I take all of my y values and multiply them by 2, right? It's the same thing we've been doing. So now instead of my graph going from 0 to 1, it's going to go from 0 to 2 and to negative 2. That was supposed to be marked pi over 2 there on that previous graph. Pi over 2, negative pi over 2. Divide these into my 4 sub-intervals. And then plot my points, right? So on the left-hand side, I start at 0, and then I go up to 1, so now I go up to 2. And then back to 0, and to negative 2, and to 0, and to 2, and to 0, and to negative 2, and to 0. Okay, now we have one last transformation, and I think this is the quickest one of all. Now we're just looking at y equals negative 2 sine of 4x plus 2 pi. And so now we're looking at a reflection over the x-axis, right? We're taking the previous y values, making them negative. So now we reflect the whole thing over the y-axis. All right, that's it. Well, that's everything that I want to cover here in our video on the Cartesian graphs of sine and cosine. So thank you for watching.